Okay, we're back for another lesson. Today we're going to do a lesson on mechanical energy with non-conservative external forces. First, before we start that, let me just review what we've been doing recently. Okay, so review. All right, so here's what we've got for our review. We've got a work equation. I'm going to put a little underline there. I got to get back used to this thing. Review. Okay, so we've got our work equation. Good old work equals F cosine theta times S. Okay, then we've got our kinetic energy. Kinetic energy equals 1/2 mv squared. And then in addition, yesterday we did potential energy. Potential energy equals mgh. We also learned that when there is no external non-conservative force, we have a conservation of mechanical energy. Okay, let me put this up here. Conservation of mechanical energy. So mechanical energy is basically kinetic energy and potential energy. So we have conserved the sum of kinetic energy and potential energy. That means that kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. But this is only true when there are no external non-conservative forces. Let's see how it does with that in my writing. Only true when there are no external non-conservative forces. Very amazing. Okay, so that's what we've done so far. And we solve various problems using that. But what happens when there are external non-conservative forces? For instance, maybe there's friction, or maybe there's the propulsion coming from a rocket engine, or a car's motor, or something like that. Then we can say that the work done. Oh, I should also talk about what is a conservative force, right? A conservative force is a force that the work that it does is independent of path. But if you go from one place to another, you always have the same amount of work. That's a conservative force. Gravity is the conservative force we're using right now. Non-conservative forces, the work done by the force depends on the path you travel. If you travel a longer path, you probably do more force. More work. Like, for instance, if a car engine or a jet engine or friction is doing the force, then you're going to have more work the farther you go, even if you come right back to where you started. Whereas with a conservative force like gravity, if you end up where you started, no work is done. So now, our new version for when we have external non-conservative forces looks like this. Okay, let me get our formula thing. We say the work done by non-conservative forces is, let me try that one more time. Yeah, I can, yeah. Let me try the, okay, so the work done by non-conservative forces is equal to basically the change in mechanical energy. Okay, so what that means is that it is the final mechanical energy minus the initial mechanical energy, right? So that's equal to the mechanical energy final minus the mechanical energy initial. The mechanical energy is just the kinetic energy plus the potential energy. So we have the work done by non-conservative forces equals the kinetic energy final plus the potential energy final minus the kinetic energy initial plus the potential energy initial. Okay, now I'm going to pause it and fix it. There, that's better. Okay, so that's basically today's whole lesson. So basically yesterday we said there was no change in mechanical energy because we were talking about without non-conservative forces. So you said kinetic energy initial plus potential energy initial was equal to kinetic energy final plus potential energy final. Now we're saying that the work done by non-conservative forces is equal to that change in energy. So it makes sense. If you do a work on the system from the outside, you're going to increase the energy of that system. So all we have to do is measure the final energy of the system, measure the initial energy of the system, subtract the two, and then we'll get the work done on the system. I guess maybe I'll write one more version of this. Let me try this one. Okay, so work done by non-conservative forces is going to equal 1/2 mv final squared plus mgh final minus 1/2 mv initial squared plus mgh initial. Let's see how that looks. Okay, I got to fix that. I'm going to pause it for a second and fix it. Okay, there we go. I went back and did it. I think that's right now. So basically what you have is you have the work done by non-conservative force is the final energies minus the initial energies. So let's try doing a problem. I'm going to try example 12 on page 178. Let's see. I need a new page. And this is example 12, page 178. So why don't you, whoops, not pose. Let me try this again. Example 12, page 178. That's better. So why don't you go ahead and get your books if you don't have them. You can pause this if you need to. Meanwhile, I'll play around with this thing, getting rid of my mistakes. So the thing I'm going to do is I'm going to do a pause, and I'm going to go back and I'm going to grab some of my equations that I think I might need. Although, maybe let's look at the problem first. Okay, so example 12, fireworks. A 0.2 kilogram rocket in a fireworks display is launched from rest and follows an erratic flight path to reach a point P, as figure 6.19 shows. Point P is 29 meters above the starting point. In the process, 425 joules of work is done on the rocket by the non-conservative force generated by the burning propellant. Ignoring air resistance and mass loss due to the burning propellant, find the speed V final of the rocket at point P. Okay, so let's see what we've got here. Maybe we can just go ahead and do this. So let's see. Mass equals 0.20 kilograms. Whoops. Let me try that again. Mass equals 0.20 kilograms. Okay. Now, what else have we got? It looks like H final equals 29 meters. Okay. H final equals 29 meters. Okay. Looks like the work done by non-conservative forces is 425 joules. Okay. Work done by non-conservative forces is 425 joules. It's pretty close. I'm going to pause it. Okay. Let's see. So what do we know? We know that the work done by non-conservative forces is the change in mechanical energy. Okay. So basically, work done by non-conservative forces equals, hold on a minute. Is equal to 1/2 mv initial squared. Oh no, we're going to start with the final. Sorry. One more time. Here we go. 1/2 mv final squared plus mgh final. Okay. I'm going to pause it and fix this. All right, let's see. That's the final. Now we do minus 1/2 mv initial squared plus mgh initial. Not too bad. Okay. So, now what are they asking us for? They're asking us for find V final. Okay, so our situation is V final equals question mark. So let's see if we have everything we need here. I think we might. We've got the work, we've got the math. Okay, now let's see. V initial, let's remember this problem again. What is it? Okay, it's fireworks shooting up. So, in fact, there is no V initial, right? It's not actually, wait a minute, let's see. We do have a V initial? Fireworks follows an erratic path, starting point in the process. Okay, it starts at rest, basically. V initial is 0. And, so okay, I'm going to cross out things that are 0. V initial is 0. Okay, H initial is 0, right? Because after all, it starts out not at any height. So really, the work is just equal to this one plus this one. 1/2 mv final squared plus mgh final. And we know everything there but V final. So, let's see where we are here. That's 425 equals 1/2 times 0.20 times V final squared plus 0.20 times 10 times 29. See how that came out. Hey, pretty good. Okay, so let me just do some stuff on my calculator here. I've got, whoops, 425 is going to be 0.10 V final squared plus Now this piece. 0.2 times 10 times 29. That's 58. Hold on a minute. Okay, so if I subtract 58 from both sides, 425 minus 58 is 367. So that means that 367 equals 0.10 V final squared. Okay, one more time. $367 equals 0.10 V final squared. Okay, cool. So we're going to divide both sides by 0.1. That's the same as multiplying by 10, so that's going to be 3670. Let me just check it to make sure. So 3670 equals V final squared. Let me try that one more time. 3670 equals V final squared. Great. So V final equals the square root of 3670 equals second square root, second answer, about 61. So that's equal to 61 meters per second. Okay. 61 meters per second. Oh my God. Okay, I'm going to pause it. All right, and if we look at the book, we see they got the same answer, 61 meters per second. So we're good. There's our answer. Okay, now I'm going to make up a problem for you to do. Okay, let me get to a fresh page, and then I will write you a problem. Here's your problem. I can use regular text. A roller coaster has a speed of 6 meters per second before it, not bad, drops 127 meters. Let's try this piece again. DROPS 127 meters. Okay. If the speed at the bottom is 45 meters per second, and the roller coaster, this doesn't look like it's going to go well, Not bad. And the roller coaster weighs 900 kilograms. How much work is done by friction? Okay, there's your problem. A roller coaster has a speed of 6 meters per second. Going along at 6 meters per second, it drops down 127 meters. If the speed at the bottom is 45 meters per second, and the roller coaster weighs 900 kilograms, how much work is done by friction? Okay, so I would like you to solve this problem. So you can pause the video and go ahead and work on the problem. Okay. You all done? Great. Here we go. Let me try it. I know that the work done by non-conservative forces is equal to 1/2 mv final squared plus mgh final. Okay, let's see. Minus 1/2 mv initial squared plus mgh initial. Not too bad. I think that's close enough. I think you can understand what I wrote there. mgh initial, close enough? Okay, so let's see what we've got here. So we're trying to find work done by gravity. That's the work done by non-conservative forces. Great. Okay, so that's all right there. We got m is 900. We got v final is 45 meters per squared. H final, okay, that's 0 because it's landing at the bottom, right? We got a v initial 6 meters per second, and h initial is 127 meters. Our G is kind of missing in there. You see the G? Let me just make sure you can see the G. Okay, so let me see if I can plug in the numbers here. The work done by non-conservative forces equals 1/2 times 127 times 45 squared minus 1/2 times 127 times 40 final initial. Okay, so that, we'll fix that for a second. Put this away. That one's not supposed to be 45, right? It's supposed to be 6. Okay. 6 squared plus 127 times 10 times, oh, wait a minute. I got to start over. So I'm mixing up. 127 is not the mass, it's the height. Okay, hold on. I'm going to put the numbers in so I can see them. Okay, so for instance, the mass is 900, right? So I'm just going to put a 900 over here. 900. Okay, so that's basically, let me get myself a little arrow. Maybe make it a little thinner. Okay, that's 900. Okay, V final. See, the bottom is 45. Okay. 45. Okay. That goes there. Okay, now we got another 900. All right. So that's going to go here. And then we've got also here, right? And V initial is 6. Okay. That goes there. G, of course, we'll call 10. Okay. That goes there. And H is 127. Okay. 127. Okay, that's our H. Now I think we maybe have enough stuff here. Let me put this up here. That over there. That there. Okay. So now maybe I can write it out without messing up. Let's try. Work non-conservative is equal to 1/2 times, try it one more time. Got to get a running start. Whoops. Work due to non-conservative forces equals 1/2 times 900 times 45 squared minus 1/2 times 900 times 6 squared. Not bad. Okay, so there's supposed to be another parentheses around this, like that, and perhaps a parentheses around this, like that. Okay, so what do we got here? 900 times 6 squared. Okay, that's going to be plus 900 times 10 times 127. And let's do that. Now, next thing I'm going to do is I'm going to make this look all neat by pausing it and redoing it. Okay, I'm back. Boy, that was hard. Okay, let's see if I got it right. Work non-conservative is 1/2 times 900, which is the mass, times 45 squared, because 45 is the final speed. Okay, so that's 1/2 mv squared final. MGH final is 0, since it ends up on the bottom level, minus initial, 1/2 times 900 times 6 squared, because 6 is the initial speed, plus MGH initial, 900, which is the mass, G, which is approximately 10, H initial, which is 127. So now it's just a matter of putting this in the calculator. Let's see. We've got, that, okay. So we've got 0.5 times 900 times 45 squared, close parentheses, minus, open parentheses, 0.5 times 900 times 6 squared plus 900 times 10 times 127, close parentheses. I get 247,950 joules. We'll go with, I'll just call it 250,000 joules. Okay, so we've got, this is equal to 250,000 joules. Okay, that's also known as 250 kilojoules. So, did you get the same answer that I did? And did I do it right? I'm going to pause and just make sure I got it. Okay, so yep, I got it right. You can take notes from that if you want, and make sure you understand how this works. And that's it for today. So all we basically have to wrap up is the work due to a non-conservative force is just the final kinetic energy plus the final potential energy. Okay, that minus the sum of the initial kinetic energy and the initial potential energy. You got to make sure you be careful with those parentheses because we want to subtract off both the initial potential energy and the initial kinetic energy. So we have to subtract off the sum of the two. Okay, that's all for today, and I'm sure that I will give you some problems to do. Bye.